recent years. Okay, so am I speaking too quickly? Is this okay? Okay, thank you. So the earliest thought of any real major tectonic significance for India-Asia collision is from the great Swiss geologist Emile Argand a century ago, who recognized that India is underthrusting beneath the Himalaya, beneath Tibet, and then there's far field effects in Tian Shan and all the way up to here, although he didn't get all the way up to here at that time. And so this is essentially a plate tectonic picture. Even though this is before plate tectonics, he mostly has something that looks like plate tectonics. And that picture has not really changed all that significantly since that time. This is basically the model understanding, although I guess at depth it's a bit different now. So these are the models that were current for the Himalaya part of this system. And this is as of 2017. And so there's some models that are on the left here. They involve the whole lithosphere. So you can see the top model on the left. This is Emile Argand's idea, again. And then when plate tectonics comes along, it's pretty similar. It's not a fundamentally different picture from what Emile Argand was arguing. And then there is one key structure that forms all of the other models, which is this fault, the South Tibet fault. It's shown differently in different models. But for the most part, this is thought to be a gigantic normal fault, a gigantic extensional structure within the Himalaya. So that's really strange. Just at face value, for Himalayan workers, we don't consider it strange because we've known of this fault since the early 80s, the mid 80s. So it's been with us for 4 decades. But from the outside view, the Himalaya is one of the world's great contractional systems, a huge contractional origin. And yet it has this origin spanning, gigantic, low angle fault that looks like a normal fault. It has high grade rocks below, low grade rocks above, a big shear zone. The main exposure of the shear zone is along the range crest, where it dips gently to the north for the most part. So looks like a big normal fault. So the main models, once this was discovered, a lot of the models, with one exception, thinking of this as like a big lithospheric scale extruding wedge, most models just went crustal. You can see that the focus of all of these models is ignoring the lithosphere. It's just looking at the crustal scale processes and sometimes looking at crustal plus climatic, like climate-driven erosion processes to understand why the Himalaya would have a big normal fault. So all of the models basically have 3 layers and 2 faults. So it's a pretty simple layer cake. There are, in all of these crustal models, there's low-grade rocks, which become the southern part of the origin. And then there's a high-grade crystalline core that is thought to extrude southwards. And then there are, again, low-grade rocks. These are Tethyan rocks, they're so-called. So it's a high-grade sequence with 2 low-grade sequences above and below, separated by faults. And in fact, the grade, it increases toward the high-grade rocks and decreases away from them. It's not super simple, but it's pretty simple. 3 layers, 2 faults. That's the Himalaya. That's what we have to explain in the Himalaya. Okay? And the major conundrum is that one of those faults looks like a normal fault in one of Earth's great contractional systems. So how we deal with that is, for 40 years, the biggest intellectual challenge. So let's start up here. This is Birchfield and Royden. Clark Birchfield, he thought that it was some sort of an extruding wedge, as if you were trying to hold a watermelon seed between your fingers and it just popped out. The mechanics, there's many mechanical models, but the kinematics are always pretty much like that. And then later on, there's the channel flow model. So the idea of this model is that this would be Tibet, and Tibet is thick, and it's piled up a lot of crustal rocks. So there's a lot of radioactive material. It gets warm. There's partial melting. And so now the partially molten material is weak. And it's weak, but it has the huge plateau on top of it. A lot of gravitational potential, pushing down on those rocks, pushing down on the weak material, squeezing it out to the sides. So the weak material might squeeze out towards the range front. And then with the onset of the South Asian monsoon, there may be extra erosion along the range front that would then pull that weak material up towards the surface and then extrude it in the brittle crust. So it would be like a conveyor belt of building up weak stuff here that funnels out to the surface. And so that's another way to get this huge normal fault. And then a model that I am associated with that was devised by my PhD supervisor, the late Ian On. I think Ian On may have visited you a few times, certainly with Professor Ulzi. His great insight was that the South Tibet detachment, South Tibet fault, is pretty flat. And it looks to him to the south, and we'll talk about this later, that the two low-grade sequences come together. And if they come together, then what happens to the fault? So he envisioned that the fault would just simply intersect this lower big thrust, which would change it from a normal fault to a back thrust. And all of a sudden, everything would be contractional. And that would make sense because the Himalaya is a huge contractional system. So this is one of Yunan's huge contributions to Himalayan tectonics. And working for this on my PhD, and I'll show you some of that, we later realized this kinematics doesn't quite work. We need to shave off pieces of the downgoing India and just accrete them slice by slice by slice. Standard duplex full thrust belt development. And then we can build the high-grade crystalline rocks that way and still have this as a back thrust. So this is where everybody was in 2015. And the idea is to try and test between these models that take the high-grade rocks to the surface in the early middle Miocene versus models that emplace the high-grade rocks at depth at the same time. So that was what a lot of our early work was about. And so the place to do this is in the Western Himalaya, because again, it's 1 layer, 2 layer, 3 layers for the modern cross-section, a few minor faults that disrupted, but nothing major. It's basically a simple layer cake, 1, 2, 3, 2 faults. And that pattern is held in the range, 1, 2, 3, the 2 faults. And that's pretty consistent along, but then here, all of a sudden you've got the top layer directly imposed on the lower layer with no high-grade rocks in between. So we sought to explain how this pattern here breaks down that way. So we went there, and this is the complex map and complex cross-section, but the simple pattern is this. We see this fault. This is the 1, 2, 3, and this is the top fault. And it gets flat here, so it's a very ugly map pattern, but it's folded over, wraps back, and intersects. So it's easier to see in cross-section. In cross-section, 1, 2, 3, and the top fault is folded and then intersects. So we see a map geometry that simplifies to something like this. We see this relationship in this area. So that to us meant that the crystalline rocks must have been emplaced at depth, so not extruded to the surface. My subsequent work after I left my PhD was to explore for this all along the range, and we found it in many locations. So here and here and here, we found that intersection of the 2 faults. So it's 2 fault planes intersecting in cross-section, it looks like a line, like a point, right? But in reality, of course, it's a line that extends along the range. And so that line is eroded here, buried here, eroded, and then intersects the surface here, intersects the surface here. So we've mapped it there. We infer from literature there. The literature, we infer there, it gets pretty close. And so we can trace that frontal intersection all along the whole Himalaya. So we think we understand the geometry a little better now. We think there's 3 layers, 2 faults, but to the south, that middle layer pinches out, the faults pinch out, bounding the crystalline core, and there you just have, to the south of that, you just have 2 layers and 1 fault. Then we realized a problem, which is inherent to all the models. Every one of those models is 2-dimensional, including ours, right? So all of those ideas are assuming that everything along the length of the Himalaya is pretty similar. And that's okay for starters, but we started to look at some of the data and realized that this was a problem. And it was a problem that my supervisor told me in my Ph.D. I went and I asked him, because I was working on this fault, I said, why is it active at different times in different places? Because the specifics of the timing is a little weird. It appears that the fault gets going around 26 MA. Something like the Leda legacy, the fault seems to start motion. But then in the west, and we don't really have a lot of time to dive into this data, so trust me on the interpolation here. It looks terrible, just like a Concordia looks terrible, right? Concordia diagram, you have the big symbols for the big errors. So the things that catch your eyes are a problem. Same thing here. What this is showing is west to east across the length of the Himalaya, and it's showing you with the gray interpolation when the South Tibet fault stops moving, when the motion is over. And in the west, the motion is over at 22, 20 MA, and then progressively, and it gets really well constrained in the central Himalaya, it gets younger and younger and younger and younger. It keeps moving until about 12 MA in the east central Himalaya. So that's a 10 million year age swing for when this fault stops motion. So if the Himalaya has only been going for like 60, 50 million years, right? If one major fault, to explain how those layers came together, has a difference in when it stops motion of 10 million years, and that difference is progressive along the range and might snap back in the Far East, that's weird. And it also means that our 2D cross-section models, they can't apply very simply to the Himalaya, because it's like 1/5 of Himalayan history is different in the activity of that fault. So we started trying to desperately think of something that would allow us to have a long strike change in when that fault stopped moving. And we also see this in some other data. We see similar patterns. So for instance, the magmatic ages in South Tibet, there are high potassium and atachitic rocks in South Tibet. And their crystallization ages are showing the same pattern of younging to the east central Himalaya. So again, this is west, center, east, west, center, east. And the cessation of South Tibet motion is similar to this distribution of ages of magmatic rocks in South Tibet, where the younger magmatic rocks are showing up in the east central portions of South Tibet. So again, there's something happening along strike that we did not understand. This is where we started to think about things differently. So the work of Anne Reclumat in Grenoble, she looked at tomography below the Himalayan system. So these are slices down halfway down the mantle of seismic tomographic imaging, so fast and slow seismic wave speeds that may image slabs, chunks of lithosphere that have fallen off from the collisional system. So this is one of them. This Tethyan slab is thought to have fallen off early in the collision. And then there's an Indian anomaly that is thought to represent a chunk that fell off in the middle of the collision, something like 25 MA. What Anne recognized, sorry, so let me place you a little bit more. This would be India. Here's the suture zone. Here's Tibet. And this, at 75 degrees east, that's the Western Himalaya. And this is progressively slices that are more to the Central Himalaya. So 85, 84, 85 is around Kathmandu. Okay? So we have a slice of the West, and then, oh, we can see that transcript. Let me try and close that for you. Can I get rid of that thing? There we go. Okay, a little better. So we're looking at slices from India to the south to Tibet to the north. Below that, from the Western Himalaya to the Central Himalaya. And what Anne picked up on is that this Indian anomaly is not in the same place in each slice. In the West, the Indian anomaly is entirely below the 660 discontinuity. But as you move more to the center of the Himalaya, the Indian anomaly is entirely above the 660 discontinuity. So this slab has fallen less far in the center than it has in the West. And Anne's inference is that it broke off earlier in the West and later in the East, so that it has progressively been breaking off. So a lateral motion along the arc of when and where the slab started to detach. So that became the basis of our idea. That gives us something that would happen differently in time along the length of the Himalayan origin. I got to get back to... okay. Did we already look at that? Yeah, okay. Good. So this is our conceptual model for what we think would have controlled Himalayan tectonics. And this is really different in appearance from all of the other models I showed you earlier, right? So this takes a little bit of understanding. One thing is actually easy for you guys. There are three things to do to think about this model. And the first thing is to imagine, and you don't have to work very hard, imagine that you are in Ulaanbaatar. That part's easy. We are in Ulaanbaatar. But imagine you are high in the sky above Ulaanbaatar. Okay, so imagine you are 1,000 kilometers up above Ulaanbaatar, and you are looking back at the Himalaya from Ulaanbaatar, but from way above it. Okay? And you are looking back at the Himalaya, and you can see through Asia. You can see through to the downgoing Indian plate. And the last thing to imagine is that it is about 15, 16 million years ago. So it's not the present day. It's about 16 million years ago. And you can see through Tibet from Ulaanbaatar, but high in the sky above Ulaanbaatar, down to the subducting Indian plate. And what the model is suggesting is what Anne was suggesting. There's a break off of the downgoing slab that happened first in the far west, and it is propagating towards the east central portion of the range. And also from other similar work, we infer that there is a second breakoff from the eastern syntaxis, the eastern end of the Himalaya, that's propagating much more slowly towards the east central Himalaya. They both would have started around 25 MA, and they both work their way in and finish around 12 MA. And so each time that this thing is propagated inwards, if you've taken off the slab, you took off a huge weight, and the origin can bounce up above it, and the dynamics of the origin can shift, and you can shut off major faults and initiate other ones. If you know critical taper theory, you're likely to shut off your contractional structures in the deep part of the origin and maybe grow outwards. So it's a likely thing to shut off the South Tibet fault. So where the slab's broken off, you shut off the South Tibet Fault. Where the slab is still connected, the South Tibet Fault is still active. So you take all of the context of the crustal models and put them above the lithospheric dynamics, and you can understand why they would operate differently along the length of the origin. So this idea and the basics of how it works is really something where in the Himalaya, we're like almost 20 years behind what they were doing in the Mediterranean. So the Utrecht group and some others in the Mediterranean have long recognized similar lateral propagations of slab detachment and the effects on topography, the effects on inflow of asthenosphere and magmatism, and some effects on the shape of the arc. This might actually give you Himalayan arc curvature. Okay, so we have complicated versions of this, but it's not terribly important for now. This is a complicated cross-sectional thing trying to connect the crustal scale kinematics with the lithospheric pattern we talked about. And if anybody's curious, we can talk about that a lot more. But the basic takeaway message is that we started 100 years ago with models that looked plate tectonic. And the models stayed pretty plate tectonic until about 40 years ago, we found the South Tibet Fault. And then everything got weird, because with the South Tibet Fault thought to be a normal fault, explaining a huge normal fault in Earth's great contractional system becomes the big task. Yin On made a huge contribution to recognize that this is not a normal fault. It's a back thrust. And then it becomes a simple contractional system. But it's a simple contractional system where the timing is not uniform along the length of the origin. The timing is different in the West from in the East Central, and it's progressive. And all of our models were two-dimensional. So we had no explanation for this timing. And so this is our first attempt at a model that can explain a rippling of crustal tectonics along the length of the Himalayan system. And thankfully, it is best viewed from Ulaanbaatar. So that's my Himalayan talk. Thank you very much. If you have any questions, I'm happy to hear them.
Yeah.
Nice. So thank you all. I hope my English was slow and clear enough. I tend to talk quickly when I am excited, so this stuff is.
I have one question.
Great.
Thank you, very interesting talk.
Thank you.
And, I would like to know the Indian and the Eurasian collision. What influence to Asian interior, including Mongolia?
All the way in, yes. So you guys know so much more about that than me. You can answer that question better than I can. So one person who would answer that question at least as well as you probably is my supervisor, Yunan. So he did some summary papers of all Asian tectonics. Running from the Middle East all the way to Japan. And so he was an early proponent of the idea that the major controls on East Asian dynamics are twofold. You have the Himalayan collision with India smashing from the south, which propagates a lot of stresses northwards. But then you also, why does it all flow eastwards is because the Pacific subduction zones are acting as a near free boundary that is collapsing to the east, allowing crustal material to flow eastwards, right? So the Pacific subduction zones and their strange dynamics of slab underthrusting and slab fall, slab rollback are probably equally as in control of the system's evolution as India-Asia collision. If they weren't equally in control, then we would see just as much extrusion to the west as we do to the east. But of course, we don't see any extrusion to the west. But again, you probably know all of this better than I do. So yes, that's my career has been focused on the Himalayan system. And then I got distracted a decade ago, and I'll show you that stuff also. I've been working on early Earth a lot. So I never got, only thanks to our Ansetseg have I been pulled this far north, because she had a very good idea. And so Ari and Mari worked together to make a big proposal, and then I helped them edit it, and then it got funded for a lot of money. And that brings us up here. But I am following these two leaders to help to teach myself and learn from you guys a little bit about Mongolian tectonics.
I have one. Do you return back to the slab detachment thing? You say, like taking an example, like we were 1,000 kilometers above UV and then seeing towards
yes.
And is it the sort of this detaching process was only starting around like 16 million years ago, or it was already sort of?
It was already, so this is in the middle of things. So if we look at it a little bit more, we can look in 2D to have a little bit more of a sense of it. There are, does this work? Is this on? There we go. Yeah, this is gonna be easier. I can only point so much. So this is 30 mm. And it's thought that for most of the system, you had underthrusting to about the Bengong-Nujong suture, halfway north in Tibet. Flat underthrusting. And this is tracked by magmatism migrating northwards. So this is not my work. This is a bunch of groups' work, probably best expressed by the Cell paper, the Cell, Paul Cap, those guys, where they track magmatism moving north, and then from 30 to 25 MA, and I think that's over about 40 to 30. From 30 to 25 MA, the magmatism sweeps back south. And so that is thought to reflect what appears in this reference frame to be rollback. In reality, it's more likely that the slab is stuck here and the origin moves northwards over the slab, such that the slab is stationary and the origin has moved north, but whatever, right? So you open up a big mantle window, magmatism sweeps back to the south, and now you've taken the slab and you put it right below the northern Himalaya. Once you put the slab below the northern Himalaya, if you think of it in critical taper terms, so just, how an origin responds to changes in the basal slope, putting a slab here probably pulls down the basal slope. And if you're pulling down the basal slope, you're going to develop internal thickening. And the South Tibet Fault might be one part of that internal thickening. So you have a motivation for internal shortening. So it probably turns on around 26, 27, according to the metamorphic records. It's hard to date fault initiation, but this is a sense of what's likely. So because there's a transition from purely burial to a mixture of burial and exhumation metamorphism. And so then after that, if we're going to go in this 3D model, we need to start looking at different sections. So the one section is in the west, and the other section is in the east center. So this section's in the west, this one's in the east center. And so here the slab breakoff happens early. And this version assumes sort of an inviscid mantle. If it's more viscous, the time would be a little shifted, but nothing major changes. So if it's inviscid, you break it off, everything pops up, the fault stops moving. And whereas here in the east, it's still connected, it's still pulling down, you still need to do internal shortening, the fault keeps going. So that's...
And then 15, and then 10.
Yeah, so
it's around like 10 million years, the east and central.
Yeah, totally. And so something striking in the east central Himalaya that isn't seen anywhere else in the Himalaya is there is a huge pulse of exhumation at around 1312, where all of a sudden you have things rocketing. You have zircons crystallized at 13 million years, 12 million years, and you have apatite cooling ages that are coincident ages. Things are just exhuming very rapidly there. And what we suspect is happening is that there is a particularly dramatic response to the final breakoff because here it's breaking off from one direction, and here it's breaking off from the other direction. There's always the side part to keep things propped up. But when it has the final break off around here, well, then all hell breaks loose for a little bit. Then it's a much bigger pop-up.
Okay, so the below part is already detached and it's like floating beneath and it just fell down.
It's just thinking, yeah. So after it detaches, that's how we get to Anne Ripplemore's image, right? So this, and this, and this, and this is the future, it's the present, but this picture, oh wait, wrong way. This picture is supposed to be 15, 16 million years ago. So this chunk here, that is that Indian anomaly, which is going to be fully detached now, and 15 million years ago would still be partially attached. So that becomes, that becomes this, is the idea. And, you know, it's just a model. We showed you lots of models. We're arguing they're all wrong, except for this new one, right? So this model will eventually probably be displaced also, but it is recognizing a problem that we have a long strike changes in timing that none of the other models explain. So it's the first model to try and explain that phenomenon, and hopefully there will be better models in the future.
All right.
Thanks for your question. Do you have any more questions? Yes, thank you.
At the beginning of your talking, you showed the cross-section map. So you mentioned the high-grade rocks squeezed out.
Yeah.
Wondering what kind of high-grade?
Okay, so some people think that they're squeezed out to the surface, and we think they're just buried. They're just so we think that each time it's a just take one little slice off of downgoing India and add it to the hanging wall. Then take another little slice. Then take another little slice and build up a stack of thrusts. So this is relatively famous rocks if you're a Himalayan geologist. It's called the Greater Himalayan Crystalline Complex or the High Himalayan Crystalline Complex. The Himalaya are, again, somewhat famous for an inverted metamorphic sequence. So across this fault, you go from biotite to garnet storolite into kyanite, selimanite, and then finally migmatite grade. The rocks themselves are mostly Neoproterozoic and maybe a little bit of Cambrian material, mostly siliciclastic sediments, and some granitoids intruded therein in the Paleozoic. So there's some Paleozoic granitoids, Pan-African granites, and intruded into Neoproterozoic sediments. And then they're all cooked. And you see, those perlithes are not singular to this unit. Also, there's very similar perlithes at the base of the Tethyan and in some of the upper layers of the Lesser Himalaya. So it's a perlithe layer that's common to all of the major units, although it's most commonly associated with the Greater Himalayan crystallines. Thanks for your question.
What was the initial collision in India and Chile?
This is the worst question ever. People have been fighting over this question. They fight and they fight and they fight, and probably 62 to 60, but the nature of the collision itself has been under debate because there are many possible indicators of what is the collision, and there's a possibility of multiple collisions. There's a possibility raised by one group that the Tethyan rocks split off from the rest, collided first, and then there's a second collision with the Tethyan with the rest of it. I am not an expert in that portion of the geology because most of the interrogation to do that work is in Tibet, and most of my work has been in India and Nepal. But there is transference of stuff that's almost certainly Asian sedimentary material onto stuff that's almost certainly India substrate at 62 to 60. So that sedimentary transfer probably indicates some initial version of collision. So I think that's valid.
яагаад асуусан гэдэг зэрэг Монгол алтай нуруунд юу гэдэг вэ? Тэр тохирол нь дээд талдаа дээд сэрдийн процесыг аваад гараад ирсэн байгаа гэж хэлсэн. Тийм байх юм бол тэр сэрдийн дээд сэрдийн үехэд үзээ юуны шахалт байсан, гямлай шахалт байсан юм уу? Эсвэл нь хойд хятадын шахалт байсан юм уу? Зааж байхгүй би.
So there is a mountain range in western Mongol outback, and there are late Cretaceous numerous rusts.
Yes, okay.
And his thought is if it was related to the far field in because
Well, I don't.
collision or China. Not China.
I think the North China. You mean the North China South China collision? Like Dabishan, North China South China should be Triassic, so that should be much earlier. Something that is important to remember for considering far field effects is that I am not persuaded that the India-Asia collision timing matters for any far field effect this far north, because the continent-continent collision is simply part of a longer-term convergence system, and the convergence is going all through the Mesozoic at least, right? Or most of the Mesozoic. So it could be a far field effect of something like an Andean collision, where you have ocean continent, but there's still in the Andes, there are, Mari can answer this better, but there's deformation 2,000 kilometers from the trench, 3,000 kilometers, 5,000.
Yeah, even sometimes the ocean can see.
Oh, in the Atlantic Ocean?
In Patagonia, yes, because
Okay.
it's much.
Oh, yeah, that makes sense. That makes sense. So there's far field deformation of an ocean continent collision. And so since there was ocean continent convergence before there was continent continent convergence, the continent continent collision timing might not matter that much for the convergence. What might matter more is just changes in plate velocities through time. That would be my guess. So yeah, it probably doesn't. If there was a lot of timing lining up, you might start thinking there's a specific importance. But since there's not, maybe it's just convergence matters.
баруун талын хэсэг нь 2000 орчим километрийн шигдээд орсон юм шиг зүүн талын хэсэг нь болохтой зэрэг нэг 1000 км орчим байдаг. Тэгээд энэ муурцсан байдаг болохтой зэрэг нэг онгоогоо тасраад яваад байна. Тэгээд тэр нь тэр урдтай болон тэр зайтай холбоотой зүйл тэгээд зөвхөн урдтай тийм бай дараас нэгэндээ 1000 км шигдээд орсон харагддаг. Баруун талдаа болохоор зэрэг бараг 2000 км шигдээд орсон байдаг. Google Earth-ээр харж байгаа шүү дээ яваад. Тэгээд энэ бас холбоотой байх юм болов уу?
So he observed on Google Earth that in western Himalaya there is a 2,000 kilometers region,
Okay.
and the eastern parts about 1,000 kilometers. So is it related to your model?
You mean the size of the Tibetan plateau?
The
The length of
range itself.
Шигдэж орсон гэж
It's sort of
Аз руу
acceleration, sort of push.
I'm sure we're.
Forward to Asia. Bring it forward to Asia.
You mean this is pushed further north?
Yeah.
Oh, okay. Yeah. So we do think the arc curvature is related to the model. Nobody has explained the arc curvature because nobody's thought it's a problem. There's a paper, actually one person did, but there's a paper in I think 2000 or 2001 in geology by Rebecca Bendick and the guy in Colorado, Bendick and Billum, Roger Billum. So they go from about here to about here, and they use metrics of curvature. So they just look at how circular is the arc. And they say that there's a radius of curvature starting from about here, and the arc is perfectly curved. But if you go beyond their points, the arc is much more curved here. It's pretty tight curvature there, and it's very straight right here. I might have some imagery about this. Let me see. So I love this question, actually. This is really cool. Let me see if I have any imagery about it. Did I just pass it? No. Give it a second. There we go. Okay. So yeah, the arc is according to Bendick and Billum, it's a perfect circle here with the emanating from a center of a circle there. But if you try and impose an arc on here, it's a much smaller radius, much tighter radius of curvature. But then this is damn near straight. So why would that be? Our thinking is based in that same Mediterranean concept. The workers from Utrecht really could track how you could impose curvature on an arc by lateral migration of slab attachment. So if you think about it here, with the slab attached, the slab encourages trench retreat. So the trench wants to move back because the slab wants to fall, right? The slab wants to fall, so the trench wants to go towards the downgoing plate. If the slab is not attached, the motivation for trench retreat is largely gone. So this part of the arc doesn't want to move, and this part wants to move that way. So then this area right here twists. So if the slab tearing is propagating very quickly, so like from west to the east central, this is 2,000 kilometers. You got the one tear goes from here to there. The other tear just goes from there to there. And it's over the same amount of time, roughly. So this one's moving quick. And this one's moving really, really slow. Which means that in this one, any one area is getting torqued for a long time and can get torqued more. And for here, no one area is getting torqued for very long. So the curvature that develops is relatively little. Because it curves here a little, then curves here a little, then curves here a little, then curves here a little. Whereas here, it's like curve here, curve here, curve here, curve here, curve here, curve here. They're all the same area. It's curved a lot. So the Himalaya has an asymmetric arc curvature, which has never been previously explained. And this model allows an explanation for it. There may be others. There's probably other explanations, but I haven't heard any. I haven't heard anybody identify it as a problem before. So I love the question. However, for your questions, we should stop because there are more talks and we get to drive together, right? So you ask me as many questions as you want, but we need to let other people, or we need to move on to the other two talks. And if we're going to move on, then I just want to let you know, you guys have a great deal of snacks. I brought some snacks from Hong Kong. So if you want one, you can pass them along. They're not too sweet. They're a little sweet. And I have 2 more boxes, so take one if you want. So thank you guys. If there are more questions, maybe just one more on this, and then Mari, do you want to give your talk, or should I give my other talk first?
I think you can continue.
I can easily continue. Yeah. I visited Nanjing University once, and my friend there, if anybody knows Wang Qing at Nanjing University, she really likes talks. She made me give 4 talks in a row, and it was super fun. So yeah, I can keep going. Okay. Would you guys like a break? Maybe a 5-minute break?